Hello everyone. It's a great honor for me to introduce our study, Automatic Extraction of Requirements Entities, by leveraging LSTM-CRF and Transfer Learning. First, we start our presentation with a brief introduction. Successful software products requires continuous changes triggered by user requirements. An effective way is to establish and maintain requirements entities, which characterize the key functional objects of software systems. Requirements entities as explicit specification of real-world objects in the requirements context, and define the scope and the functions to be implemented or enhanced in the software. Additional benefits are reported to support new requirements identifications, requirements change analysis, and effort estimation. In existing studies, there are two categories of approach, rule-based and learning-based approach. However, for the rule-based approach, which leverage natural language processing tools and linguistic rules, the natural language processing tools are trained on the general dataset, which result in a poor performance under domain-specific contexts. For learning-based approach, they require lots of training instances which are expensive to label. In these studies, we propose an approach named RANO, which explores LSTM-CRF network and transfer learning. RANO is evaluated on an industrial dataset. The results show that RANO could achieve promising results and outperform the baseline approach. Then we introduce the LSTM-CRF network used in our approach. LSTM-CRF network is a widely used deep learning models. There are three layers in the network: the embedding layers, LSTM layers, and CRF layers. However, LSTM-CRF network requires a large size of label data for training, which limits its application to domains with a shortage of label data. Next, we introduce the proposed approach. RANO consists of four phases: model constructions, LSTM language model training, LSTM-CRF trainings, and requirements entity extractions. The first phase is the model constructions. In this phase, RANO explores LSTM-CRF network. In order to elevate the problem of limited label data, RANO constructs an isomorphic LSTM language model. In the language models, the embedding layers and LSTM layers are the same as the LSTM-CRF network. The softmax layer is to compute the probability of a word given the previous word sequence. The trained LSTM language model could obtain the linguistic knowledge. The second phase is the LSTM language models training. First, RANO pre-trains the language model with the general corpus. This step is to obtain the general knowledge of natural language. Second, RANO refines the language model with the unlabeled requirements, with the purpose of adapting the knowledge to requirements context. The third phase is LSTM-CRF training. First, RANO builds the training instance with the labeled requirements. Using the BLO labels, RANO annotates the location of each requirements entities. Then, RANO transfers the embedding layers and LSTM layers to LSTM-CRF network, frees the model parameters in the two layers, and only train the CRF layers with the instance. Finally, using the trained LSTM-CRF network, RANO extracts the entities for new coming requirements. We first introduce the dataset. The dataset includes two different corpus, general corpus and domain-specific corpus. For the general corpus, we choose Wikipedia as the data source and randomly sampled 12,000 articles. For the domain-specific corpus, it is collected from our industry partner. The details are shown in the table. Next, we introduce the research questions and the results. In RQ1, we compare Rhino with three state-of-the-art approach, including a rule-based approach, a supervised approach, and an unsupervised approach. The results show that Rhino outperformed the three baselines with a performance of 81% precision, 79% recall, and 89% F1. RQ1 is for the transfer-learning evaluations, where we investigate the contribution of each step in Rhino. We conduct the 4 sightings, where we remove each step in Rhino and investigate whether each step could boost the performance. The table shows the performance and the different sightings. The results show that the transferred knowledge could improve 12% precision, 7% recall, and 10% F1. In RQ3, we train Rhino with different sizes of unlabeled requirements and labeled requirements. The figure shows the performance and the different size of unlabeled requirements and labeled requirements respectively. The results show that 2,500 unlabeled requirements and 1,000 labeled requirements are the reasonable numbers for promising results. In RQ4, we apply the Rhino in 11 new projects and conduct expert review. The table shows the performance of entities extracted by engineers and Rhino. The result indicates that Rhino achieved the precision and recall both at 81% and outperformed the manual extraction by engineers. Finally, we conclude our work. We propose an approach for requirements entity extractions. Evaluation results from an industry dataset show that Rhino could reach promising results. Besides, we verify the value of general corpus and unlabeled data and provide an effective practice to make use of this data. Future work includes similar requirements entity clustering and automatic entity relationship constructions. Thanks for your listening.